Now that you know how to write the names of different compounds, we're going to go in the other direction and we're going to write the formulas. So in this case, I'm going to give you the name and you're going to write a balanced formula. We're going to start with the covalent compounds, again because they're easiest. Remember, we're looking at two non-metals and we're looking to write a compound based on the words and the prefixes given. We're not looking at charges. Our first example is silicon dioxide. Now if you look, silicon is on the left side of the line that designates the metalloids, and I told you that anything to the right of that is a nonmetal. Silicon is a part of the metalloid group, which means it can be a metal or a nonmetal depending on the situation. In this case, because you have the prefix di, you will know that it's acting like a nonmetal, and so you will name this like a covalent bond. Silicon, there's your abbreviation, Si, oxide, O, and di, 2. Nitrogen, here on the nonmetal side, fluoride, nonmetal side. Nitrogen is N, fluoride F, and penta is 5. Our next example, diphosphorus pentachloride. So we're going to look at phosphorus, P, di, 2. Chloride, Cl, penta, 5. Our last example, monocarbon, carbon which is a C, mono means 1. You can put the 1 here if you want to, but you don't have to because it's understood. Iodide, I, tetra, 4. So as I said, you can leave the 1 if you want. The more correct way to write it is like that. Writing the chemical formulas for the covalent compounds doesn't get any more difficult than this, and so now I'm going to move to the ionic compounds. Ionic compounds really aren't that difficult. You just have to look at oxidation numbers and make sure that they balance. Balance meaning that they cancel each other out and equal 0. So we're going to start with strontium arsenide. Strontium is here, Sr, and it's in the +2 column, so I'm going to put a +2 up there. That's a +2 oxidation number. Arsenide, remember ide means it's a compound, so we're looking for arsenic, which is over here, As, and it's in the -3 column. We need these two, when you add them together, to equal 0. That means that our compound is balanced. You can tell that it's not balanced because we're not going to have a 0. What that means is we're going to have to add additional atoms to our molecule to get that 0 to happen. Mathematically, we're going to have to multiply the oxidation numbers. There's nothing that you can multiply -3 by to get a +2. Nothing you can multiply 2 by to get -3. So you have to find a number that they will both go into. And that number, of course, is 6. So -3 times 2 makes a -6. I'm going to squeeze that right there so you can see the math. And 2 times positive 3 is going to make a positive 6. Well, 6 and negative 6, when added together, equal a 0. So these numbers are going to go right here at the bottom. So when I write it clearly, you have SR3AS2. And what this means is this molecule has 3 strontium atoms and 2 arsenic atoms. And together, all 5 of those atoms equal a charge of 0. Potassium, way over here, K, in the column with the +1 oxidation number. Nitride, so we're looking for nitrogen, -3. And again, we're going to have to add some atoms. So I'll put this right here, put that right there. If you did 3 times 1, you're going to get a -3. If you did 1 times 3, you're going to get a +3, and they'll cancel out and equal 0. So we'll move those numbers down. There's the 1, and squeeze that 3 in there. And again, written clearly, K3N, because that 1 is implied. So again, this means we have 3 potassium atoms and 1 nitrogen atom for every potassium nitride molecule. Our next examples are going to include multiple oxidation numbers, and that's the Roman numerals here. Okay, so same thing, titanium, we're going to look for that. Here it is in this multiple oxidation section. So I'm just going to write Ti for the moment. Phosphide, so we're looking for phosphorus. Put that there. Phosphorus, -3. Notice I haven't put anything here yet. If you look, titanium is in the +2 section. That's the default. But I said I want you to use +3. This means use this particular oxidation number, not the default. Well, lucky for us, +3 and -3, when you add them together, you get 0, so your final compound looks just like that, TiP. Cobalt, this tells you that it's multiple oxidation numbers, so you kind of know where to look. There's cobalt, CO. I'm telling you use the +2 version, which just happens to be just like the default. Selenide over here, which is selenium, Se, -2. And again, when you add them together, it equals 0. So that's all you have to write. We'll do 2 last examples. Gallium over here, so Ga and a +3 charge. Oxide, you already know oxygen, -2. And again, we're going to have to add some atoms so that it equals 0. Again, 3 and -2 can't be multiplied by anything in order to get each other, so we're looking for that common number, just like we did at the beginning. So we're going to look for a 6. -2 times 3 will give us -6. 3 times 2 gives us a +6. Move those numbers down. Ga2 O3. Last example, zirconium. If you're not sure where to look, that 1 is going to tell you it's in our multiple oxidation section. So there's zirconium right there, Zr, and this tells you use a +1 oxidation number, not the default. Carbide, which is carbon. Now, carbon's in the +4, -4 section. But we've got an ionic compound. Metals in the front, non-metals in the back. Plus here, so this has to be -4. Again, we've got to do some math so that we get 0. -4 times 1. It's going to give us -4 on that side. 1 times 4 will give us +4 on that side. So we're going to cancel out, move those numbers down, write it nice and clear. Zr4C. Remember that 1 right there is implied. Doesn't get any harder than this. The most important part is making sure that these numbers are balanced and that this Roman numeral is applied to the metal and not the non-metal.